For our second example of computing surface area, I want to talk about how we can manipulate the two formulas a little bit. And so let's go ahead and look at y equals x cubed from the ordered pair 1, 1 to the ordered pair 2, 8. So I grabbed this graph off of Desmos, and we want to take this curve and we want to revolve about the y-axis. And then find the resulting surface area. So find the resulting surface area. So if we were to do that, we are going to actually end up with, I'm just going to grab my pencil here. So we're going to end up with, let's see here. I'm going to get this, see if we can get this graph. Let's actually do it in black. And we're going to end up with a solid of revolution. It's going to look something like that because we're going around the y-axis. Okay, so if we go around the y-axis, we end up with a solid revolution, looks something like that. We want to compute the surface area. And so we can reference back to, and I just grabbed our notation over here, we can reference back to the formulas that we derived for the surface area. And if we're going to go about the y-axis, let's zoom in on the y-axis right here. And if we're going to go about the y-axis, keep in mind that we're going to be looking at this formula. Now, what I want to talk about is this idea of kind of manipulating the formula and thinking about which ds we want to use, because we can actually use either of the two forms of ds when we're doing these formulas. So that's going to depend on if we want to integrate with respect to x or want to integrate with respect to y. Now the formula, we're going around the y-axis, so we're going to be looking at 2 pi x. So if you look at the picture here, this is representing the radius of our bands that we're computing the surface area from. So we want to utilize that formula, the 2 pi x ds. But ds can be either the square root of 1 plus dy dx squared dx, or ds can be written as the square root of 1 plus dx dy squared dy. All right, so keeping that in mind, and we're utilizing, all of that is coming out of this, using this relationship. So I'm going to go back to our example, and let's talk about which way we want to do this. So which way do we want to do this? Well, if we want to compute the surface area is going to be the integral from c to d 2 pi x ds. So let's take a look. We got y equals x cubed, and we can integrate this with respect to x or with respect to y. So doing that, let's come down here so we can actually write them in two options. So we have two options right now. One option, x is equal to, so remember we're starting with y equals, we can't see that anymore, so I'll rewrite it. Y equals x cubed from 1, 1 to 2, 8. So we could start with x as a function of y, since we're going around the y-axis. X equals, if I just manipulate that, take the cube root of both sides, x equals y to the 1/3, and that would be bounded between y equals 1 and y equals 8. Okay? So that's one option. And our second option, and I'm going to do this one over here, our second option would be to continue to think of it as y equals x cubed, bounded between x equals 1 and x equals 2. Okay, so those are the two ways that we can think of that actual line, that little curve segment that we've rotated. So those are the two ways we could think of it. If we're thinking of it in terms of y, x equals y to the 1/3. Then the setup for the surface area, we're going to need dx dy. So the derivative of this is going to be 1/3 y to the negative 2/3. And our surface area formula is going to be the integral from 1 to 8 of 2 pi times x, but our x is y to the 1/3. Okay, so y to the 1/3 times the square root, because remember we're going to be integrating with respect to y, so we can't have mixed units there. So I have to replace the x in the formula with the definition of x. X is y to the 1/3. And then this is going to be 1 plus, and then we're going to have 1/3 y to the negative 2/3 squared dy. I'm going to make a little squiggly line right here so that we keep those two separated. Okay, so let's just continue. This is a little messy. I like to simplify my integrals. I want to get this simplified so we can see what sort of integration strategy to do with this, and then we'll go back and we'll look at the second option and see what we would do with the second option. So continuing down here, this is going to be equal to the integral from 1 to 8, and let's actually pull that 2 pi out. Put the 2 pi on the outside of the integral, y to the 1/3, and this is going to be actually the square root of 1 plus. I'm going to write that as 1 over, I'm going to square it. It'll become 1/9 when I square it. It'll also become y to the negative 2/3 squared, which becomes negative 4/3. So when I drop it down, y to the 4/3 dy. And then I'm going to find a common denominator. So just coming in here, I'm going to add those two fractions, just keeping up with the simplification here. So I'm going to add those two fractions. I've got a little image right there that I'm saving for later. Okay. All right, sorry about that. And so then we're going to have 2 pi, still got that y to the 1/3. This is now going to become, when I find that common denominator and add those two fractions, 9y to the 4/3 plus 1 over 9y to the 4/3. And even though that denominator has a fractional exponent, it is a perfect square. So I'm going to just keep with the algebra here and continue to simplify, simplify, simplify. So here we've got 2 pi integral from 1 to 8. We've got our y to the 1/3. We're going to have the square root of 9y to the 4/3 plus 1 over 3y to the 2/3 dy. And I see I can even go further now because I can reduce these y's, again, fractional powers, but still just applying rules of exponents from algebra. So I end up with a 1/3 y to the negative 1/3, or 1 over y to the positive 1/3. And then I've got the square root of that numerator. But while I'm looking at that numerator, I'm just going to rewrite it in a way that might make the integration strategy a little easier. I'm going to write it as 1 plus, and then I'm going to have 3y to the 2/3 squared. And you can see that. Okay? And I think that makes the integration strategy that we're going to do next a little more obvious, because now you can see that this piece right in here is a 1 plus u squared. And since that integration is going to end up being, well, it's going to end up being a trig sub after we make the u substitution. I'm going to do it in 2 steps. Feel free to do it in 1 step, but to be clear on these notes, I'll do that in 2 steps. I actually want to do it in 2 steps with the u sub for when we compare to the other side as well. So pulling the 1/3 out, so let's just keep going. We'll do our u sub first, but just a little bit of a simplification here. Let's pull out, so we'll have 2/3 pi, and then the integral from y equals 1 to y equals 8. But we're going to make a u substitution here, and the u substitution that we're going to make, u is going to be equal to 3 y to the 2/3, so that du would be, so 2y to the negative 1/3 dy, just taking the derivative, and then du, actually, let's do this. Let's divide off by that too. So du over 2 is actually equal to y to the minus 1/3 dy. And that's right here. So I can make that substitution on my next line. And this is going to become, we already pulled out the 1/3. Sorry, I keep popping up that. We already pulled out the 1/3. So this is going to end up being the square root of, we're going to have a 1/2 from the substitution on the du. So 1/2, I don't even need my square root, doesn't even need to be that long. Square root of 1 plus u squared du. Now, these were y equals 1 to y equals 8. So on this next line, I want to go ahead and change my bounds. 1/2 times the 2/3, we end up with just pi over 3 for my constant. And then let's change the bounds to get them in terms of u. So if u equals 1, I'll show that work down here. So if y equals 1, then u would be equal to 3, plugging it in. And if y equals 8, then u would be equal to 3 times 8 to the 2/3. But remember that that is actually just the cube root of 8 squared. So we've got 3 times the cube root of 8 is 2, so 2 squared, and that ends up being 3 times 4, or 12. So just kind of showing that calculation rather than just saying it out loud. U, so we can make our changes on the bounds. U is equal to the lower bound, it becomes 3, and the upper bound becomes 12. And then this ends up being the square root of 1 plus u squared du. Okay, so now at that point, we would want to make a trig substitution. So we made the u substitution up here, and now we want to make the trig substitution. So here was the u substitution, and now we're going to need to make a trig substitution. So for the trig substitution, 1 plus u squared is going to be a tangent. So we'll let u equal the tangent of theta. To do that, of course, we'll let tangent run from, on its bounds, restricted bounds from negative pi over 2 to pi over 2. And then my du is going to be equal to secant squared of theta d theta. And my triangle for the back substitution is going to be, if this were theta, then this would be u1, and this would be the square root of 1 plus u squared on the hypotenuse. Okay, so now I can make those, I can make that substitution. I wrote my bound calculation right there, so I'm going to bring this down here. So this is going to be equal to pi over 3. Now, I am going to say this. I could look at the bounds. I could look at changing the bounds to be in terms of theta. But this, just glancing at those, u equals 3, if I were to think about actually plugging u equals 3 into u here, it's going to become the inverse, theta is going to become the inverse tangent of 3, and if I were to plug 12 in, it would be the inverse tangent of 12. I don't know that that's all that helpful. Those aren't ones that are my special angles, so I wouldn't be able to have, like, say, a pi over 4 or pi over 3 or pi over 6. Those don't fall into that category, so I would have to either use a calculator to get an approximation on those, or just carry the exact values all the way till the end to get my exact answer here for the surface area. So I'm going to instead use the triangle to get back in terms of u, and then I can just plug in my u bounds. So that's how I'm going to approach this problem. So finishing this out, this is the integral from u equals 3 to u equals 12. And actually making that trig substitution, now I have the square root of 1 plus the tangent squared of theta, secant squared of theta, d theta. And continuing down here, this is going to be equal to pi over 3 from u equals 3 to u equals 12. Now, this piece in here, the whole point of doing the trig sub was that this of course, becomes the secant squared of theta, and we're taking the square root, so that becomes the absolute value of the secant of theta. And we'll star that, and just once again, our restriction on the domain of theta allows us to drop the absolute values on the next line and multiply by secant squared. So this actually becomes secant cubed of theta d theta. Okay, so bringing that all the way over here, because I want to write out my secant cubed formula. Again, we've proved that, and we've utilized this secant cubed quite a bit. So I'm going to just jump right to the integral of the secant cubed is 1/2 secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. And we're going to evaluate that from u equals 3 to u equals 12. Okay, so pi over 6. And now we got to get this back in terms of u. And unfortunately, let's see if I can scroll down and get my triangle here. Oh, it's so close. I think we can get it in the upper corner of the screen right there. So glancing here, I'll just pull it all the way down, then we'll go back. So if you look up here at our triangle now, so here's our triangle, we're referencing back to that triangle right there. If you take a look, that triangle, we need the secant and the tangent. So the secant is going to be the square root of 1 plus u squared over 1, the hypotenuse over the adjacent side, and the tangent is going to be u over 1. So putting those expressions for secant of theta, tangent of theta. So this is going to be the square root of u squared plus 1 times u plus the natural log of the square root of u squared plus 1 plus u. Evaluated from u equals 3 to u equals 12. We could probably drop at this point we're back in terms of u, so I'm going to drop the carrying of u. So this is from evaluated now from just 3 to 12, knowing that those are u's. Okay. All right, now we just have to plug those in. So this is pi over 6, and then when I plug in 12, I'm going to get 144 plus 1, so that's going to be, well, it's actually going to be 12 times, I'll move the u to the front. It's going to be 12 times the square root of 145 plus the natural log of the absolute value of the square root of 145 plus 12. That's a positive quantity, so I don't actually need to take the absolute value. I can put that in parentheses. Minus, let's do the minus underneath, minus, and then we're going to have 3 times the square root of 10 plus the natural log of the square root of 10 plus 3. Again, positive, so I can drop those absolute values. Okay. And I'm gonna go ahead and leave it like that. That is our answer in terms of simplification. We could maybe do a little simplification on that, pull the natural logs together into a quotient. The roots are not like roots, so we just have those roots. All right. Okay. All of that though, and I wanted to go all the way back, if we could, scroll all the way back to our other option. And our other option was to do this as y equals x cubed, from x equals 1 to x equals 2. And so just as a comparison, I wanted to set up what would that actual surface area formula look like compared to what we did here. So here we had, this was our formula that we ended up after plugging it in for this particular function. That's what our surface area integral looked like. Well, what would that look like for this option if I had done it this way? And so if I had done it this way, our dy dx would be 3x squared. Now our surface area calculation, we still need to do surface area. Since we're going around the y-axis, the surface area still needs to be equal to the integral from c to d of 2 pi x ds. Okay? But remember that ds can be written as either of these two roots that are written right above at the top here at the bottom of our formula box. So since I can pick either one of those, if I'm working with a function defined as a function of x, then I could use this ds representation, and I can integrate with respect to x. So if I'm going to integrate with respect to x, everything needs to be in terms of x. So zoom out so we have just a little bit more space. So then if I wanted to leave the function y equals x cubed instead of rewriting it, I can do that. And then this ends up just being the integral from, now remember, we're integrating with respect to x. So from x equals 1, this curve that we rotated, if we're looking in terms of using x here, it was defined from x equals 1 to x equals 2. We're going to have 2 pi times x. Now we're not going to change that because we need it to be in terms of x. So we're not going to rewrite that in terms of y. So 2 pi x, and then the square root of 1 plus, and take our dy dx, 3x squared, and we're integrating with respect to x. Okay? Okay. So I just want to pause for a second right there and scroll back to what we had highlighted here, right? Here we had highlighted the surface area formula, and we have it all in terms of y, and it looks good. We did a good job on that. We took the derivative, and then we did a bunch of simplification, and then a u sub. So coming back over here, I just want you guys to notice on this particular one, I'm going to also do a u sub, but I don't have any simplification to do. Excuse me. I don't have any simplification to do because this right here is pretty clear to me that that's a 1 plus u squared. And so I don't have a whole lot of simplification. I don't have any simplification to do. I can just go right into the u sub. And so here, if I do the u sub, let's just look at this real quick. U would be 3x squared. Du would be 6x dx, or x dx would be du over 6. I can make that substitution. So if I make that substitution right there, I end up with, pull the 2 pi out. We're integrating, I'm going to change the bounds here, so I'm going to leave the bounds off for just a second. The x and the dx are going to get replaced by du over 6. So I've got 1/6 times the square root of 1 plus u squared du. And I'm going to change the bounds. So this one I am going to just talk through. So if x equals 1, just looking back up here, u would have to be 3. And if x equals 2, u would have to be 12. Now, if you just watch that last full example, those u bounds look awfully familiar. Quick little simplification with the 2 pi and the 1/6. And I end up with pi over 3, integral from u equals 3 to u equals 12 of the square root of 1 plus u squared du. Notice that that integral right there, we might have to scroll down a little ways here, but that integral right there is the same integral that we worked with when we were over here doing our substitution. We will get the exact same answer. So that's what I wanted to illustrate right there, was that it turns out that, here we'll even bubble this in, it turns out that we always have the choice. We can decide how we want to manipulate the ds when we make the substitution to either simplify our work or streamline it a little bit for the calculation, if we want to integrate with respect to x or if we want to integrate with respect to y. So notice that this was the same integral from option 1. So it was the same integral from option 1. We're going to get the same exact answer. It just was possibly an easier way to do it, where we didn't have to work with fractional exponents. Okay, I've been carrying around, this has been one of my longer videos, but I've been carrying around this funny little math joke I just wanted to end with. The Wi-Fi password is on the back of the router, but the router is a Mobius strip. So you know, you gotta enjoy a little bit of math humor after a long example here. All right, guys, hope that helped to show you how to use either of those two DS representations.